My name is Curtis Brown, and I am joined once again by Tom Dick, Steve Kokoska, and Vicky Carter. I'm super excited to have them on here tonight. We're going to be looking at transforming sine and cosine functions, doing a little bit of exploration tonight. And so I will not take any more time other than just to remind you that the problem set is down in the description, so you can go grab those problems if you haven't already and follow along. Steve and Tom and Vicky has got some great tips, so can't wait to hear them. Steve,
All
take
right.
it away.
Thank you very much, Curtis. How's that? Can you see that screen? Is that working tonight?
It is working.
All right, wonderful. We've got some good problems for you tonight, Curtis. Vicky, Tom, it's wonderful to be back with you again in 2025. Curtis, I hope you've done your homework tonight because we do have some good questions for you. I know you'll be monitoring the chat, but we've got some good questions for you.
Well, hopefully there'll be some answers in the chat.
All right, well, here's the first one. We're going to suppose that f is a sinusoidal function and the graph of y equal f of x is shown in this figure. I apologize, Curtis. I don't know how well this is showing up on the screen, but there is actually a grid in this figure. Certainly when we post the PDF pages, the grid does show up there. Again, I'm not sure how well this is showing up in the figure on the screen, but we'll do our best with it. So eventually, when we get to the end of this, what we'd like to do is to produce a formula, an expression for this sinusoidal function, but we'll work our way through that here in pieces. And all we can do for now is to answer some of these beginning questions visually by using this figure, by using this graph of y equal f of x. So let's see. The first question here is, what's the period of f? Well, I'm going to be a little nerdy, Curtis. I'm going to pull up my ruler here. Here is a way to do this. So a way that I looked at this is, well, I'm going to try to draw a horizontal line through y equal 1. And I'm not sure exactly why that looked good to me, but I tried to do that. So let's see if I can get this to work here with my ruler. There we go. There it is. So I drew that horizontal line at y equal 1, and I tried to see, well, where does this graph begin to repeat? And I can see a little bit of that grid there, and it sure looks like to me that it starts to repeat over here at x equals 6. And so I concluded by looking at that figure that the period P is equal to 6. Now, there are certainly other ways to do this. We could certainly go from the peak to another peak. That seemed to be me a little bit more inaccurate because if you look at those peaks, they don't really, well, they don't really lie on a grid line, a vertical grid line. So I felt a little uneasy about that. So I think I've got the period at 6. What's the amplitude? Well, a way to do this is to find the peak and the valley, to find the highest point, the highest y value, and the lowest y value. Find the total distance between them, and the amplitude is half that. So I think I found the peak up here at 3. I found the valley down here at -1. And so the difference between the two, well, that's the distance between those two values. So that's 4. And I divide by 2, excuse me, to get the amplitude. So I'm on my way to looking for this, to getting this formula. So what I'd like to do is to arrive at a function, at a formula like this, that will describe that figure up there. And so here's what I did. See if I can arrow up just a little bit. I know that the period P is equal to 6, and I think the best way to remember this is that the period has got to be 2 pi divided by this constant b out in front. And so if I set 6 equal to 2 pi divided by b and solve for b, let's see, I bring b to the left-hand side and divide both sides by 6. And so I think I've got b equal to pi divided by 3. I think that's correct. The amplitude is equal to 2, but I'm going to be a little bit careful here. In examining that figure up above, it certainly seems like what I've done with the original sine function is that I've actually reflected that over the x-axis. And so a is going to be actually -2 to not only take into account the amplitude, but that reflection across the x-axis. So let's see, I've got b equal to pi over 3. I've got a equal to -2. And I've got to carefully again look at that figure and see that, you know what? The sine of x has actually been shifted up 1 unit so that d is equal to 1. Now, it turns out here that there is no horizontal shift. If you just think about shifting that sine function up 1 or down 1 from the figure, you'll see that it goes through the origin there. There is no horizontal shift. So I'm going to put all of this together. I think an expression for that figure would be there's a -2 is equal times the sine of b times x, pi over 3 times x. Again, no horizontal shift in there, plus the vertical shift 1. That's kind of cool, and that's kind of a neat way, I think, to work through this piecewise. I'm going to show you one other figure here before I turn it over to Tom. Curtis, I'm not sure if you can see all the colors in there, but there are quite a few. What I like to do sometimes is to try to show how I might arrive at that function f by successive transformations. And I apologize, I might not have all of them in here, but let me take a look at least at a couple. If you can see this green curve, I believe that's this one right here. That's the curve that I would start out with, which is y equal to the sine of x. Now there's a curve very close to that, and I think in my figure here, it might be kind of brownish. And you can see that that's just, well, it almost looks shifted just a little bit, but what's happened there is that the period has changed from really 2 pi to 6. Those periods are very, very close. And so this figure that's right close to that one, or pardon me, this graph right here, is a y is equal to the sine of pi over 3 times x. So that's all in the argument. Now, if I could do this in a nice compact way, I would actually draw some arrows. Tom's seen me do this on a couple of occasions where we do transformations. What I like to do is to kind of pick a point on the original curve, which in this case would be the sine of x, and show how it gets transformed, show how that curve moves. So what I've done first is to change the period. Now, the next thing I'm going to do here is I think I'm going to work to this figure right here. So that's my sine curve, my sine of pi over 3x, but it's got an amplitude of 2, and it's reflected about the x-axis. So that curve is actually y equal -2 times the sine of pi over 3 times x. How about that? And then finally, what I would do is a vertical transformation. I would transform, shift this up 1 unit to finally get this curve, which was y equal to -2 times the sine of pi over 3x plus 1. And I probably beat that one into the ground, Curtis. I'm sorry about that.
That's okay.
But what?
There was a great comment that was made when you said, well, there's no horizontal shift. And one person put in the chat, no horizontal shift? Or is it that there is no reflection? And yes, there's a horizontal shift. And I think I love you could write this one with a horizontal phase shift and no reflection, um, and get the same graph.
Get the same curve. Yes, there are other ways to look at this. Absolutely right. Yeah.
So
And I think I would
love
I would
the
Curtis challenge students to try
Yes,
others.
absolutely.
yeah to come
Absolutely.
up with write this as with a horizontal phase shift rather than the reflection.
Yeah.
What do you do to kind of make that happen? Another one, writing this as both the sine and then turn around and, well, what if I wanted this in the form of a cosine?
Cosine curve. Absolutely. Yep. Absolutely.
Write this in the form of a cosine curve.
Yep.
All of those things are good exercises in the transformations.
Yeah. Vicky, have you seen any questions, practice questions, where you might be given a periodic function like this, which is either sine or cosine? And it might be multiple choice, but some of them contain a cosine function and some contain a sine function?
Um, I think so, but I'm not sure off the
Okay.
top of my head. Of course, this is a huge focus of FRQ3, where
Yeah.
they're having to kind of look at a graph and then they are working with a contextual scenario in order to come up with the coordinates. But I think the practice of doing this is very beneficial, kind of for both kinds of questions.
Yes.
I think
Great.
most of the questions, to give them a graph like this, and instead of giving them the full function, it's like find the period or find the amplitude or
Yes.
something like that, where they kind of pinpoint a specific part of it to look at.
Okay. Tom, how about a little technology here?
Sounds good, Steve.
Okay. There you are, sir.
Right. Right. Okay, I'm going to try to share my TI-84 screen with y'all, and
Got it.
that has come up. And this problem Steve's been looking at, he's really done that really nice analysis, essentially just looking at that graph. The calculator could come into play as you're working on problems like this, is to perhaps confirm, if you think you've got the function, plotting it to see if it fits the curve all right. And I'll even go a step further. Steve, I think, focused in on some key points on that graph. And so we might even plot those points. So I'm going to go actually to the stat menu and edit and get into my list editor there and actually enter some of those points that Steve was reading off the graph. And I'll add a few of my own, I think. So one that was pretty clear was the y-intercept. So that was 0. Put that in L1. And in corresponding y value in L2 was 1. So that was our y-intercept. And it looks like it goes through, there's a 0, I think, right about at 1/2. So I'll put in 0.5 for my x and 0 for y. And just kind of work across. I think the low point on the graph was at 1.5, I think. It looks like it. I'm kind of eyeballing this, but
Yep.
As you said, there is a grid there. It might have show up faint on your copy, but you can read these points pretty carefully. So 1.5, we've got -1.
Yep.
And then another, oops, let's get down there. About 2.5. Looks like it crosses the x-axis again. And then the next point that's pretty clear to me, it won't be equally spaced at all. I'm going to go all the way to 4.5 because that looks like that's where that high point was.
Okay.
And that was at what, +3?
Good.
And finally, looks like at 6, it was equal to 1 again.
Good.
Yeah. And just for grins, I'll put one more in. It looks like there was a 0 at 6.5.
Okay.
So lots of points there. Really, the key points are going to be the kind of the midpoints of the curve, kind of where those inflection points are, and the high and low points. But we've got a lot of points here. And if we actually plot these, let me go to the stat plot. excuse me, let's see, second, there we go, stat plot, plot one. Let me enter that. Turn that on. Looks like it's actually set up the way I wanted. It has the first two lists kind of by default, L1 and L2. And I'll even do to graph it, let me go into the zoom menu and do zoom 9, which is zoom stat. And there's those points plotted. Okay, so what we're after is to come up with a curve that will fit those points. Now, if I go to y equals, I've gone ahead and entered not a specific function with the values determined for the amplitude and whatever. I actually put it in the form that was presented on the question itself. It says, find something of this form, a times sine of b times the quantity x minus c plus d, okay? And when you do that on the TI-Nspire, something to keep in mind is these constants here, a, b, c, and d, they're never empty. They always have some value in them. I'm not sure what these values are. Why don't we just go ahead and graph it, see what it looks like? Maybe we can guess it. Yeah, go ahead.
Can we make one change to that? So
Sure.
in the AP pre-calculus, they use x plus c.
Okay. Yeah, why not? All right. So let me go over.
Because we are kind of hopefully targeting some students and an audience tonight. So
okay, so I'll edit that minus c to a plus c. Okay. And let's enter that. And let me just graph it. And you know, I think this is just a regular sine curve. Okay. And we can check that pretty quick. Why I'm saying that is, or is it? Let's see.
Right.
yeah.
Is it? Let's see. Why don't we do a trace here?
Well, I don't know. You've got ones. Oh, we don't have the transform app running.
Not yet. Not yet.
Not yet. Yeah.
Okay. Yeah, in fact, let me go ahead and just go to pi. I'll just enter pi for x. Okay, so at x, looks like it's 0. Well, that would make sense for sine x. And it's going up to 1 and minus 1. Yeah. Another way to see what the current values for A, B, C, and D are is we could just quit the graph and just call those values up. Let me see what was, whoops, sorry about that. Let me try that again. Let me do a quit. All right, so let me do an alpha A. Looks like it's 1, alpha
Okay.
B, 1, alpha C, 0, and alpha D, I'm going to guess is 0. Yeah, okay, so that really was just a regular sine curve. Now,
So,
Vicki mentioned the transform app. Go ahead, Vicki.
no, I'm just kind of curious. Did you store those values ahead of time?
I did. I
When it-
just went ahead and stored A, B, and C, and D.
So
Well,
a word
So I
of
would be
caution.
starting with that regular sine curve.
Yeah.
I
So
was going to I was gonna say I smell a trick here, folks.
So,
Tom,
Tom,
Well, notice I didn't put in the answer values.
that's true.
Tom may have set us up with a sine curve to begin with, rather than just.
so Tom, did you also set the window?
Actually, for that window, I
Because it
think I
landed me
just
right on
used
top.
zoom stat, so it fit that those points that were plotted.
You probably use MStat, yeah.
Yeah, he did zoom stat.
And I just left the window, so it fit those points that we plotted, those individual points. It
Yes.
gave me a fairly nice window for that.
So go back to graph for 1 second.
Sure. Yeah.
So it almost looks like it's in units of pi over 2.
Very close. Very
Isn't
close.
it? Yeah, how about that?
Yeah.
Okay. Interesting.
Now, Vicki mentioned the Transform app, and that's just a beautiful app. It's resonant.
Tom,
Yeah, go ahead, Kurt.
We did did get a question, just a clarification on how to store values.
Oh, okay.
So if you want to show folks, you can do that real quick.
Yeah, just real quickly, if if looking at it, look like I want to change the amplitude from 1 to 2, let's store 2, and the store key is just 2 keys over to the left from 2. You see that store button, and I'm going to store that in A. All right, and now let's go ahead and graph again. We can see that we have increased the amplitude of that curve to double what it was before. Similarly, I could store a new value for B or C or D, and then regraph and kind of sequentially, try to seek out, okay, what do I need to do next to make it fit these points? So, for example, I think Steve's strategy at this point might have been, you know what, instead of 2, I want that to be my amplitude, but I think flipping it upside down will make it fit better. While somebody in the chat said, well, maybe shifting it over would make it fit better. I think both of those strategies are totally viable.
Yep.
Another way you can control these constants, the A, B, C, and D, really nicely is with that transform app. So I think I'll turn to that, show that off. So I'm going to go to apps, and it's not on the first page. I'll just keep scrolling down until I see transform. There it is, the transform app. We hit enter there. We get this kind of title screen. And I want you to pay attention to something. It says for animated graphing, which we could do. I tend to just kind of look controlled, some nicer graphs, but without them being animated. It has the XRES as 3. It says set XRES equal 1 for default graphing. XRES equal 3 will give you kind of choppier looking graphs. So that's something we will probably want to do. Now it says press any key. I'll just press enter. And if I go to Y equals, note that beside Y1 and Y2, we have a slightly different symbol beside those. And those are showing me that these two functions, Y1 and Y2, are active under this transform app. Okay? So let's go ahead and graph this again. And notice the different look here. I've got the same graph I had before, but it's showing me the values of A, B, C, and D. Okay? So if you enter a function involving any of the letters A, B, C, and D as constants, it will set up those for you to control their values at the bottom of the screen. Now, the way right now it's active on A, and if I was to hit the left or right arrow, it will increase the value of A. Or if I hit the left arrow, it'll decrease the value of A. And we can even go into negative values. So I think Steve said he really wanted it to be -2. Okay, let's go ahead and make it -2. Now, if you want to change to one of the other constants, you just hit the up or down arrow, and it'll cycle through. So if you kept hitting just one arrow over and over again, it would go through all of them. So I'll hit the up arrow. Notice it went all the way over to B. So let me go back to B. And so now we can put in a value for B here. If I just hit the left or right arrow, it's going to increment B by an integer amount here. So you can see I'm changing now the period by manipulating that B value.
Mm-hmm.
But you can, if you've analyzed it and you've come up with a really specific value of B that you want to try, you can just enter that. So I'm on B here. I'm going to go ahead and enter the value Steve came up with. I think it was pi over 3.
Yes, sir.
So let's see. Pi is right on the keyboard here. Let's do pi over 3. And notice it's changed it to a decimal. Okay.
Mm-hmm.
And let's see. C is 0 here, and I think Steve's C value was also 0. He didn't have any additional term in there. I think all that was left was to shift this up 1 unit. So let me go over to the D value. And I think if I just hit the right arrow key, it will increment up 1. Boom, there we go. We've got this really nice fit there. So I think if you've got, and because these are such an important part of that AP pre-calculus curriculum, is looking at these general sine functions and cosine functions, entering them into this form, whether or not you use the transform app, that's going to be very handy for changing the values of A, B, and C, and D, rather than re-entering an entire function equation each time. You can just enter these values. I find the transform app just fascinating because as you're changing those values, you're actually seeing those sequential transformations that you're making.
So Tom, let's
yes.
make A a +2.
All right. So let me hit the up arrow to get over to A. And I'll be lazy. I'll just hit the right arrow to increment, since it's a nice integer value that you want. Okay.
Okay, because someone suggested if we used a +2, we then could have a C value that wouldn't be 0. And so since our period is 6, I think we might need to move this 3 units.
Okay.
And coincidentally, we could go 3 to the right or 3 to the left. So let's try C is 3.
All right. And then this one, I'll do it the quick way. I'll just enter 3.
Okay.
Boom.
Yeah, I like that.
And then we could try -3.
Okay. Oh, it's broken. Nothing happened.
Oh, that's
you know what's
beautiful.
really interesting is visually when we made those changes, Vicky, as I was looking at the graph, it looked like it was reflected vertically.
Oh, okay.
Even though what we really were doing was translating horizontally.
Yeah.
But that's just more just substantiating that those things are equivalent in terms of how they affect the graph. So
yeah. I mean, I love this because again, if you challenge students to try various forms, then they've got a quick and easy way to check to make sure that each of the forms that they've come up with is actually accurate. So
yeah,
I love this.
And something else I'd point out real quick is Steve made a remark about how close the graph of sine of pi over 3x was to just regular sine x. Well, we can kind of see why. Look at that b value. Pi over 3 is pretty darn close to 1. So that's why it is so close. Yeah.
So kind of a cool.
I interrupted somebody. Go ahead. Yeah.
Kind of a cool exercise then, Vicky. Maybe you've seen these two is a graph with a set of points, and use this transformation app to fit a sine or a cosine function to those points. That's kind of neat.
Yeah,
and we discovered that there may be several ways to do that.
Yes.
Great.
Good exercise.
I'll stop the share there unless there's something in the chat, Curtis, that we should try to address.
I haven't seen anything in the chat.
Okay, I'll stop the share and turn it back over.
That transformation graphing app is sure a handy tool.
Yeah, very nice.
Exploring the.
Okay, great, Tom. Let's take a look at number 2. This one is a little similar. Here's the figure that shows the graph of a trig function. And what I'd like to do in this one is to find an expression for f of x that's in this form, actually using a cosine function. So let's see if you can see the grid here. The vertical lines, I believe, are every pi over 8 units. So the horizontal lines are at the integers. plus or minus 1, 2, 3, and there's a 4 up top there. But the vertical lines, I think, are every pi over 8. So let's see. The first thing I focused on was the period. Can I figure that one out? Well, if I take a look carefully at these grid lines, I'll see that there's a peak right here at this point, which I believe is pi over 8. And the next peak occurs, so one cycle here occurs right here. And if I know these grid lines are pi over 8 apart, I believe that's 9 pi over 8. So let's see. Recognizing that, I think I can figure out the period by subtracting those two values. So the period here is going to be pi. So using that same formula from problem number 1, we know that 2 pi divided by b must be equal to the period. So I can solve for b and get that equal to just plain old 2. Now, since we want to get an expression using a cosine function, it looked to me like there was a horizontal translation of the cosine function pi over 8 units to the right. So it looks to me like C is going to be equal to a minus pi over 8. I'm sorry about that 2 in there. The amplitude, well, like I did in problem number 1, I've got to find the peak and the valley here, and it looks like the highest value of y is 4. The lowest value is minus 2, so the difference is 6. Divide that by 2, so the amplitude is 3. I don't see a reflection here, so to me, I believe that's saying that A is going to be equal to 3. And let's see, I think there's a vertical shift 1 unit up. When I factor in that amplitude of 3, I've shifted up this function, this graph, 1 unit. So in my constants up there, I think D would be equal to 1. So let's see, if I put all of this together, there's A, the amplitude 3, no reflection this time. There's B as a result of finding the period of pi. Here's an indication of the horizontal shift, and here's an indication of the vertical shift. Pretty cool. I think, Vicky, that's sort of a typical kind of a problem in AP pre-calculus. We'd like students to be able to look at a pretty detailed graph like this and determine those constants A, B, C, and D, if you'd agree.
Yes, and I mean, again, I think it's really good practice for students to do this. I do want to mention one thing. Your approach, your students want like a one way to do something. And sometimes there are multiple ways to look at things. So if you could just go back to your graph a second,
Sure, sorry about that.
that's okay. I don't know if you remember, and if students are participating tonight, on the previous problem, Steve drew a horizontal line at y equals 1
Correct.
because it was a little more obvious in that graph, that particular graph in number 1, that that is kind of that's that midline. This
Yep.
one, it might be a little harder to see the midline because it doesn't coincide like the midline coincided with that y-intercept, which was 0, 1. This one doesn't. You could still use the midline here to find that period.
Mhm.
It just was more natural, perhaps, to look at the maximums, the tops of the peaks, to find that period. But you could also look at those low points and do the same thing. The
Sure.
key here is realizing that that interval from 0 to pi over 2 has the 4 subdivisions, and that those grid lines are at pi over 8. That's really the bottom line, no matter which of the methods you use to find the period.
Cool. All right, down at the bottom here, I'm going to leave a little bit for our students out there and teachers and students especially tomorrow morning at 8 o'clock. Here's my attempt at successive transformations to get to the graph of y equal f of x. I think I've got what, 1, 2, 3, 4, 5 in there. So here's for tomorrow morning at 8 o'clock. See if you can write an expression for each one of those graphs and somehow determine how did I get from y equal the cosine of x to eventually this expression right here. So that's kind of cool. I think all the grid lines are in there as above, and I think I've got 5 separate functions in there, eventually getting to the one up above, and see if you can figure out those transformations. Pretty cool. Okay, Tom, should I take a look at another one?
Yeah, I think so. I want to leave
Okay.
plenty of time for that, especially for that application problem.
Okay.
Yes.
Okay. So number 3 here is similar to, I think, one of the typical free response questions. And this one is modeled after Knoebel's amusement park. It's one of the best family amusement parks in the country. They're routinely rated for the best roller coaster in the country. And they have a beautiful actually 2 wooden roller coasters. And they have this wonderful restored carousel there. And this actually has it. Do you remember if you're on the outside horse, you can go around and pull that golden ring? They actually have that on this carousel. It's very cool. So, all right, these model horses are on this carousel. They're arranged in a circle of diameter 36 feet. At time t equals 0 seconds, a certain model horse is the greatest distance from a fence at the entrance to the ride. So this is going to take a little bit of explanation. And I'm going to draw a picture on the next page. But as you look at that carousel in that picture, think about walking into this ride from a fence in front of you here. So the perpendicular distance from that model horse to the fence at the entrance into the ride is 44 feet. The next time that model horse is in that same position is at t equal 12 seconds. So the carousel spins around, and what we're going to do is to measure the perpendicular distance from that outside horse to this fence. Yikes. So this sinusoidal function h models this perpendicular distance in feet as a function of time t in seconds. Wow. All right. So let's take a look at the next page here. So at the top of this page is kind of this typical picture. Help me here, Vicky. Don't let me make a mistake here. But this is kind of the typical picture or figure that we see in this AP Pre-Calculus FRQ. Is that correct?
That is correct. That is the diagram that will be shown.
That will be shown. Okay.
That is it. Yes.
That's the one. Okay.
That's the one.
All right. So sort of at the middle of this page, I've kind of tried to translate the words on the previous page, drawn a picture of this carousel, and here's where my horse is at t equals 0. So the diameter of this carousel is 36, and if you read carefully here, the distance from here to this fence was 44 feet. And so if I've done everything correctly here, the distance from here to here would be 8 feet. And so now what's happening is the carousel is spinning. I'm going to put in an arrow here. And the carousel spins, and there are sort of these at least 4 important points. And I want to try to figure out, well, what are those points F, G, J, K, and P? I wonder how come they're not alphabetical all the time. But anyway, what do those correspond to? And let's see if I can figure that out. Well, let's see. That dashed line is sort of the midline. And so I kind of see that as corresponding to where my horse is at that point or at that point. F is the farthest point from the fence. And so that's going to correspond to t equals 0. And let's see, what's the distance from the fence there? Well, it's 44 feet. So I think that F has the coordinates 0, 44. Now remember, this makes one complete cycle in t equal 12 seconds. So I'm going to cut that in fourths. So let's see, right here at time t equal 3, what's that distance? Well, let's see. This distance from here to here is going to be what, 18? And then I've got another 8 over here. So that's going to be 26. So at time t equal 3 seconds, the y coordinate is 26. Another 3 seconds goes. The carousel or my horse has moved down to this point, kind of this low point, the closest to the fence. That's time t equals 6 and the distance is 8. Another 3 seconds goes by. I'm over here at t equal 9. Well, that's got to be the same distance from the fence as G, so that's got to be a 26. And then finally, in another 3 seconds, it reaches this point P up here. I'm back up at the top, and my distance to the fence is 44 feet.
So
Wow.
that is nice. So one of the strategies that I think a lot of teachers have tried to help students with is to find the coordinates of F, which
Yes.
in this particular scenario were fairly easy to come up with. And then they find P because they know it's going to have the same, in this case, height, but
Gotcha.
they're just using that period, which is the 12.
Okay.
And then they go to the halfway point, J, which is the lowest point, and then they do the 2/4.
Gotcha.
So it's a different strategy, and it's totally like what the students see. But I
What
think
feels
that has,
comfortable?
yeah,
Uh-huh.
what they're comfortable with. I mean, I really like the way you did it because it corresponded so nicely to your little diagram. But I think that other method may help some students that are having, especially when the time gets to be fractions. And we
Yes.
know what fractions can do to people sometimes.
Yes.
And so that may help a little bit.
Okay. Good advice. Very good advice. Okay, I got a couple more questions about this problem. I'm sorry, Vic, Tom, that I couldn't fit all of this on one page, but here we
It's not
go.
even on one page on the AP exam, so you're fine.
Okay. All right. Well, this function h I claim can be written this way, and I'm sorry I used small letters here, A, B, C, and D. And I want to see if I can find those values. Well, let's see. What's the amplitude here? Well, again, the high point is 44, the low point is 8, and so that distance between those two is 36. I divide by 2 to get the amplitude as 18. What's the period here? Well, the period is 12. We know that because in the statement of the problem, it said it was back to that original position after 12 seconds. We can also confirm that by finding those points on the previous page. And I've actually written them in at the top of this page. So we know the period is 12. And once again, at least for the third time tonight, we use this formula. 2 pi divided by b has got to be 12. So that tells me that b has got to be equal to pi over 6. This one's a little tricky here, but I think there is actually a horizontal transformation here. I think it's actually 3 units. And let's see if I've got that right. Let's see if I've got that right. I think it is actually 3 units. Let's see if I can confirm that. Yes, because I'm using the sine function here. So let's see. I want to make sure that I'm at the peak over here at time t equals 0. So I would be transforming this 3 units. 3 units, I think, to the left.
And I know some students have actually, like, they come up, even though it's not a designated point, it helps them a little bit to come up with the coordinates of that point just to visualize that horizontal shift, that phase shift a little bit.
Okay, good.
That left-hand point.
Okay, good. This one over here.
Hmm.
Okay, good. Very good. And let's see, I think this graph has shifted up. The sine function is shifted horizontally 26 units to
That
get
would
me
be
to that
vertical.
midpoint. Pardon me,
Vertically.
vertical shift. A vertical shift 26 units to get me to that dashed horizontal line. So holy Toledo, I put all of that together with my A, B, C, and D, and I believe that's an expression for my function h. So I won't do this. I'm Tom. I'm not suggesting that you do it, but this is another one where we could actually put these points in that stat list editor and double check to make sure, not only using the transformation app, but actually just using a plot function, right? Just a y equal menu and putting this one in to make sure that it fits.
Yeah,
Cool.
and I think that would be a really good class activity that students are verifying. But please note that on the AP exam, this is FRQ3 and it is a no calculator question. So you're just using the calculator perhaps in class to kind of get a good feel for what you're doing and maybe checking your work when you have
Yep.
homework or something like that.
Which I think, Vicky, I'm glad you brought that up, is something that maybe we've lost sight of here. I remember many years ago, we thought of using the calculator as exploration and
Hmm.
confirmation,
Yes.
and we've sort of lost that a little bit. So yeah, very good. Good point.
Yeah, and I still do it a lot. As a matter of fact, I checked my homework this afternoon.
I, I do too. I do too. Okay, I've actually got one more question about this application here. So we're going to think about that graph of H in part A, and we're going to call the t-coordinate of G T1, the t-coordinate of J T2. So I'm actually looking at what's going on between these 2 points, between G and J. And the first one says on the interval T1 to T, which of the following is true about H? And Vicky, help me on this, but I think this is sort of a typical question on that
Yes.
FRQ also.
Yes, it is.
Okay.
And
And
it's
so,
essentially a multiple choice question in the middle of a free response
response
question.
question, yes. Okay, so I'm just gonna, as t increases, what's happening along this curve here? And if I just look at that, I can see that, well, I know that h is still positive. The values of h are still positive. They vary between 26 and 8. But they are indeed decreasing as t increases, as t moves from left to right. And so the answer here, or the choice, is part B. Pardon
Yes.
me, is response B.
Yes.
And another possible question here is describe how the rate of change of H is changing. And that always sounds kind of funny to me, but how is the rate of change of the rate of change of H changing on that interval? Well, I believe the way that they would like students to answer this question is to examine the concavity. And so I think the way that they want us to look at this is to notice, well, the graph of H is concave up on that interval, and that's a signal that automatically tells us that the rate of change of H is increasing on that interval T1 to T2. I'm going to scribble just a little bit because I know lots of AP pre-calculus teachers also teach calculus. And so, okay, Curtis, I got to ask you a question here. If H is concave up on that interval, what does that tell me about H double prime, the derivative, the second derivative? What does that tell me about H double prime?
If it's concave up, it should also be positive, right?
Good. So H double prime of T would be greater than 0 on that interval. If that's true, let's kind of work backwards a little bit. What does that tell me about H prime of T? Since H double prime is greater than 0, what does that tell you about H prime of T?
I don't know. I have to think about that.
Well, that means it would be increasing because
It's
its
Increasing.
derivative is
increasing,
positive.
right?
Yeah,
Yeah.
because its derivative is positive. So
Because the derivative, yeah, because its derivative is positive, so it's increasing. Yeah.
very good. So for those teachers out there who are doing AP Calculus also, there's a very nice connection there. And Vicky, we were talking a little bit earlier about maybe there's a change in wording coming here.
It is, we've gotten some feedback that there may be some wording changes. And teachers, if you have not looked at the sample questions for AP Pre-Calculus that are in Blue Book, you may want to do that. There is a wording change on this one in Blue Book, and it is the CED free response question. So it's questions that you've already had access to. The way the new one in the Blue Book is worded is on the interval from T1 to T2, describe the concavity of the graph of H and determine whether the rate of change of h is increasing or decreasing. These wording changes supposedly are to help students be very focused and know exactly what they've got to say. And I think it's a good thing because it can be a little vague. Like, what do they want me to say when it says
Yeah.
describe the rate of change, how it's changing? So now you're going to name the concavity, and then you're going to say whether that rate of change is increasing or decreasing. And the concavity is going to basically tell you what it's
Tell
doing.
you what's going on. Yep.
Yeah.
Very cool. Okay, we're going to shift a little bit here, Curtis. We don't have too much time left, but we're going to shift a little and take a look at a different kind of problem here. Number 4 says find all the values of theta between 0 and 2 pi that satisfy that equation. So I'm going to try to solve this analytically, and then I'm going to take a look at this with a calculator, and then I'm going to turn it over to Tom. Maybe he can do a little bit with the TI-84. Tom knows I like to use the Nspire, so we'll get there. So let's see, I'm going to set these two equations equal, and what I'm going to do on the right-hand side here is I'm going to use a trigonometric identity. I think there are actually a couple different identities that I could use, but I chose the one so that I could get everything in terms of the cosine of theta. That seemed like a very reasonable thing to do because I've got a cosine of theta on the left-hand side. So, okay, let's see. I used the identity and then I distributed that -1 all the way through. And then what I did is I brought the -2 cosine squared theta to the left-hand side. And I apologize for this, Curtis. I've sort of violated one of my rules here. I'm going to scribble a little bit off to the right-hand side. I believe a better way, a more precise and a more general way to solve this problem is the following, okay? I might come back over here and I'm going to rewrite that as 4 times the cosine squared of theta -1 equals 0. I believe a better way to solve this is to try to factor this. And this is actually a difference of 2 squares.
Yeah.
And so to write that as 2 times the cosine of theta -1 times 2 times the cosine of theta +1 equals 0. And then in order to solve this, I'm going to use the principle of zero products. And in this case, I'm going to arrive at the same values over here, but I think this is a better way to solve it. And here's a reason why. If you reach this point as a student, under the pressure of a high stakes exam, there might be an issue with just saying, oh, well, I'm going to take the square root of both sides and I'm just going to get the cosine of theta is equal to 1/2, and I'm going to lose a couple of solutions here. So I think the more correct way to do this is to try to factor that expression, use the principle of zero products, still arrive at these values, cosine of theta equal to 1/2. The two values in my interval in question there are pi over 3 and 5 pi over 3. And yes, I think in this class that students must be very familiar with common angles in the unit circle. Cosine of theta equal to -1/2, where does that happen? Well, theta is equal to 2 pi over 3 and 4 pi over 3. Terrific. I'm just going to, I'm sorry, go
Yeah,
ahead.
just real quick. Students also, when they're solving these trig equations, which are very likely going to happen on FRQ4, need to pay very close attention to the interval that you are given and make sure you stay within that interval. And in this case, it was 0 to 2 pi.
Good. I'm
But
going
it
to
won't necessarily always be 0 to 2 pi.
It will not
It will
always be
not.
0 to 2
It
pi.
will not for sure, Curtis. That's correct. I'm going to show you a quick way that I solved this on the TI-Nspire. Here's what I did. I probably overkill here, but I defined a function f, I defined a function g, and then I used the TI-Nspire function solve. It says solve f of x equal g of x for x. If you can see it on the very end, there is that vertical bar, which I read as such that, or so that x is between 0 and 2 pi, and it actually comes back and solves this expression. It actually gives me the numerical values here. Sometimes when I solve these problems with trig, I actually do get symbolic answers. I'm not sure what the cutoff point or what the gray, that line in the sand is, but I have these 4 values. Another way that you could solve this is actually graph these two functions. And I did that on the right-hand screen. And what I did on the right-hand side is I actually analyzed the graph on the TI-Nspire and found those 4 points of intersection. And luckily, I think they do agree with my values on the left-hand side, on the left-hand screen. So that's kind of cool. Tom, do you want to show us a little bit with the 84?
Sure, that'd be fine.
Okay. Beautiful.
All right. So let me bring my TI-84 screen back up again. And I'm essentially just going to take that graphing approach that Steve mentioned, but with just a little bit of a wrinkle. And this is a standard thing that students might do when faced with an equation like that they're trying to solve. Is what Steve did was graph each side of the equation as a separate function. What we could do also is manipulate the equation so that one side is 0, and then just graph one function and look towards 0. So let's just take a look at what that would look like. I'm going to just go ahead and clear out my y1. And if I think if I do my calculation, let's see, the left-hand side was 2 times the cosine. And I'll use x as my independent variable, and that quantity was squared.
Yep.
The other side was negative cosine of 2 theta. If I add that to both sides, we're going to get a plus cosine of 2x. And that's my one function. And now I'll be looking for the zeros that function. So let me
Tom,
enter
before
that.
you leave that screen,
Yes.
the students that are on tonight, pay close attention to how he typed in cosine squared x. You have to embed it in a set of parentheses in order to get the correct syntax to make the
Expression, yeah.
calculator graph it.
Yeah, very good point. And it's somewhat enforced a bit because I think the cosine gives you that left parenthesis, right? You know,
Yeah.
as soon as you hit it. So you couldn't get that 2 in there very easily,
Right.
even if you tried. But yes,
But
this
some
is
will
really
try.
what that shorthand means.
So,
All right, so I'm going to
Tom,
graph this.
I meant Tom, Vicky.
Yeah.
So if you did not put that extra left and right parentheses in where the square is, and the square was just after that right parentheses after the x, how does the calculator interpret that? As x squared?
Well, I think if it's, I'll tell you what, let's just go ahead and, let's see if I delete that parenthesis. Is that what you're thinking?
Yeah, so what happened there? So delete that one, and then of course delete the left one too, way over there.
Far left one, right? Yeah,
Yes,
like
please.
that. I'm sure, pretty sure that's going to be interpreted correctly. I'm kind of force of habit. I make
Oh, I hear you.
ample use of parentheses just to make absolutely sure. But I believe, yeah, the priority here is that function application will be first, and then it'll square. So
Okay.
we should be in an okay shape.
Okay.
Now,
That's correct.
For graphing, when you're graphing with trig functions, a window that you might consider using, and I'm going to use it here, I'm going to go to the zoom menu, and you see number 7 down there? It's zoom trig. Let's go ahead and select that, kind of see what happens with that. So I'll hit enter for zoom trig. Now this is not going to look like the graph Steve had because he graphed each side of the equation as a separate function. I've combined them. Wondering what these hash marks are. Let's just look in the window and see what it's done. Oh, look at this, the X scale. That's where the marks are on the x-axis. That number looks pretty familiar to me. It looks like pi over 2. So those tick marks are exactly at pi over 2, spaced apart. So returning to the graph, we could now calculate some zeros. And let me move over close to the first 0. That's pretty close. Let me make sure I'm to the left of it. There we go. I'll hit enter and right bound. Let me move a little bit to the right of it. And now give it a guess somewhere in between. And it homes in. And you know what? I've seen this value already before tonight. That looks like pi over 3, right? Okay.
How about that, huh?
So there's pi over 3, and I believe that was one of the values.
Yeah.
And we would just repeat this routine for each of those zeros. So I would call it 0 again and pick off the ones that are between 0 and 2 pi.
So
By
the
the
only
way,
thing,
the left and
yeah.
right bounds of this window, I believe, are from -2 pi to +2 pi. So it's a really nice window for trig functions. Go ahead, Vicki.
No, I was just going to say when you actually, I would do a zoom trig just like you did, but I would also go to window and I would probably set my X min at 0. And that X max is a little bit larger than 2 pi.
Oh, you're right.
So,
I misread. Yeah, you're
yeah.
quite
So
right.
I would
Because I
actually
forgot that the
set it,
hash marks are actually pi over 2 apart.
yes.
Yes.
But I
So
would
this
actually physically make it 0 to 2 pi, the window that we were given, to make it very obvious that there are 4
that's a
X
wonderful
intercepts.
suggestion.
Yeah, and so you don't have the problem of perhaps picking up an incorrect 0.
Yeah,
Right.
ones that are
So-
outside of where we want to be. Yeah.
I did have one question that came up, and I know we're right up against the time, but I want to make sure that I ask it. And that is that how do limits help us understand the behavior of sine and cosine graphs during transformations, such as when their amplitude and or frequency changes?
How do limits?
Limits?
That's the question that came in.
Well, we haven't talked about anything about limits here this evening. I don't think, Vicky, help me here. I don't think there's any limit expression required associated with sine or cosine.
No, not really. I mean, unless somehow there was, I don't know,
Yeah,
possibly a piecewise function with a trig function as a piece that I really don't kind of see that happening, to be honest with you.
the language of limits would come into play with once we started looking at things like the tangent function or cotangent.
Oh, definitely to
cosecant.
describe
So they
the
have vertical
asymptotes.
asymptotes.
Yes.
And the flip of that is when we get to inverse trig functions, there are some horizontal asymptotes to some of those functions. So maybe that's the motivation behind that. Yeah. So limits would come into play with some of the other trig functions.
Yeah.
But for the sine and cosine, really, I mean,
No.
we're just doing we're really just doing the transformations as we did tonight.
Yeah.
Looking at how amplitude, frequency, phase shift, and translation up and down kind of impact the graph of sine and or cosine. Really good question though, maybe for calculus, to kind of come back and think about that. So when we get to our maybe one of our Monday night calculus sessions, we can think about those limits that way. I just want to make sure that I remind teachers that they can hop on to an email and ask for professional development hours. I've got a certificate that I'm happy to send anybody who would like that. So I'll pop my email here in the chat. And then I think our next session is roughly a month from today.
3 weeks, I think.
3 weeks.
3 weeks. Okay. Well, that's roughly a month. Okay, it's a little sooner than a month from today.
Yes, February 13th.
February 13th, the day before a very important holiday, Valentine's Day. And also wanted to make sure that everybody was thinking about and made aware of that 9 days before that. So February 4th, there will be another AP pre-calculus webinar on the Texas Instruments webinars that you can sign up for. So if you email me, I'll make sure that you also get a link for that as well. So you can sign up for that webinar and get to talking some more. I think when we come back, we're going to be looking at a little bit more in this sine and cosine space of the more periodic function type stuff. I think that's right. We're going to be looking
looking
at
at those
the
functions that Tom,
other trig,
yeah, the
The other
other,
trig function.
the ones Tom
the
mentioned a few
other
minutes ago.
trig function.
Right.
Yes, some of those functions that Tom mentioned a moment ago. So, well, we're really excited to have everyone here, and thank you guys very much for your evening. Take care, and we'll see you in about 3 weeks.
Bye, everybody.
Bye-bye. All right.
That was terrific, guys.